Welcome back to lecture 9 of EMTH 4. We are still on the topic of discrete probability distributions, and we are continuing with the topic of binomial distribution. And up next would be the Poisson. Let me just share another screen because we are going to deal with a spreadsheet software, which is another way to work with probability distributions. Well, it has the necessary functions, and well, if you're going to refer uh, to the mathematical capabilities of this spreadsheet software as functions, okay, and we're going to deal with that. And let's go back to our example a while ago of the die throwing event. Let us recall that we have an event X, okay, and then we have 6 events, and we could get immediately the mean of this one by using the average function, which is just to get the average of this 6. Okay, please take note of that formula. You could see also the formula in this function bar. All right, we now have the probability of each event as p p x equals x. All right, and then it's very basic. It's all right. Sorry, it should be 1/6. You just have to make use of the change of the set setting of this variable. It's going to be a number, so it's 1/6. Okay, and it becomes 0.17. You just drag this so that you have the same probabilities for each and every event. Now we want the weighted mean, right? So we write here weighted mean, and to get that we will need we will be multiplying the probability of each event, the value of the event. Okay, and that would be denoted by x multiplied by the probability of x equals x, and that would be this column times this one, and just control D this one so that you get, okay, the exact formula of the first column down to the very last. Now you want to get the weighted mean, and it's just averaging, oh no, it's summing up sum of all the values of this column, and it's the same. You have 3.5. Now to get the standard deviation, we now use, wait, am I speaking or not? Oh, probably I am. Okay, I'm not really sure. Yeah, it's recording my voice. Okay, so this will be, well, the formula of the standard deviation is the square root of the square of x, the quantity x minus mu x, and well, we want to get it directly solved, but in the time being, we just make use of this one, right? So you have ux, right? And so we have the character mu, refer to UX. Okay. This is a subscript. Okay. Also this one. All right. Get the, you want this multiplied, or you want this squared. Okay. 2 superscript. All right. Now to get this one, you just subtract this, the value of the x by the weighted mean. So to make the B9 steady, what we're going to do is we're going to press F4. Okay, so introduce those characters, the $sign. That means it will be as it is. If you drag this down, take note that it will not change, but the other column or cell will change depending on the uh, uh, specific column it is referring to. And we want this squared, so we just take this one and raise it to squared. Again, Control D, and we now get the sum of this value. And then we get the sigma x. Okay, sigma x. That is the standard deviation. This is just the square root of, sorry, that's the square root of this one. All right, so the final value would be 3.5 plus or minus 4.183. That's another way to solve that problem. Now let us proceed with the discussion. I'm going to the sharing of the PowerPoint slide. Right. First to discrete probability distributions. And now we go to the discussion of binomial distributions. All right, we have the definition of a binomial distribution describing the number of successes in a fixed number of events, like the rolling of die or drawing of cards. We have identified previously that the probability of all the events in rolling a die have equal chances of occurrence at 1/6. That is a given. With the binomial distribution, what we want to know here is the probability of getting the correct event in a small number of events of rolling the die. This is important because we do not have the luxury of time to do a lot of trials. As I was saying, you could do this 100 times, 1,000 times, and even infinitely, or doing it without end, and still will have the same answer as predicted by the probability. And in the case of research, we want to make sure that a significant amount of trials is probabilistically enough to ascertain that the results are indeed indicative of the real outcome or the general outcome of that event. So you have the definition over there. The binomial distribution describes the probability of having exactly k successes in n independent events with a probability of success p. The number of scenarios is multiplied by the with the probability of the scenario. The number of scenarios is the number of ways to arrange k in successes in n trials. Okay. The probability of n is what has been previously identified for a single event. So that is n. we have n, sorry, we have n over here, right? We have n, and here is k, and we have p. We have already discussed them. Again, the k successes in n independent events with the probability of success p. Okay, and you have the formula for the binomial distribution. Okay, this is another notation for um, n taken k. Okay, you have the combination of n taken k, and if you could see, that just is simplified as the equation of the combination equation. Okay, right there. This is equation 1 again. Okay, the probability of n is what has been previously identified for a single event. The events should be equally probable as with coin tossing or drawing cards, depending on the successes. Drawing a card independently is equally probable with all the rest of the cards in a deck. The probability of a binomial distribution as defined is the combination of events in n taken k multiplied by the probability of the event multiplied again by the probability of failures of all the events. This is shown as equation 1 a while ago. The requirements to solve for the probability of a binomial distribution are again denoted by n, k, and p. Very confusing because in agriculture you have the NPK, nitrogen, phosphorus, and potassium. So the mean and the standard deviation are also obtainable from the given. We have the mean as mu is equal to NP, and the standard deviation is, all right, NP times, the standard deviation is the square root of NP times 1 minus P. All right, we have an example here. All right, I think I slipped out of this slide. I was going too fast. But anyway, we are here now in this example, and we have the given of a problem. What is the probability of rolling 2 3s in 6 rolls of a die? Pardon the grammatical error here, but it's a sample in English. Anyway, so 6 is the n, k is 2, and the probability of, again, given, it's the same for all events in a die rolling event. And so we can now solve this by, okay, we have the formula, the n taken k times p raised to k times 1 minus p raised to n minus k. That would be 6 factorial, okay, 6 factorial over 2 factorial all over 6 minus 2, the quantity factorial, times 1 over 6 raised to 2, which is k. And we have 1 minus 1 over 6, the quantity n minus k, which is 6 minus 2, which is 4, right? That's the simplification. We simplify because, again, this is going to be 4 factorial. So we simply remove this one, and this becomes 6 times 5. That's why we get this one. And it's simplified as 6 over 6, and you get 5 over 6, which you raise to the 4, and you get, simplifying this one, you get the probability of, let's see, 0.2, right? That's a probability of rolling 2 threes in 6 rolls of a dice. Now, let's go to the Poisson distribution. For the Poisson, this is another type of discrete probability distribution. This is named after the French mathematician Simon Denis Poisson, who is also credited for the Poisson. Well, you're going to go through that in your strength of materials, the Poisson ratio. Okay. This distribution expresses the probability of a given number of events occurring independently and with a known mean rate in a fixed interval of time or space. Take note of this keywords rate and fixed in a fixed interval of time or space, which means this is volume and yeah, this is time, temporal, right? This is spatial or volume. Now, we also take note of the word here, independently, which means the events do not mingle or they're independent of each other. Okay, so in the formula, we have, or the notation, we have, if you could see the graphs, you have lambda as the mean rate. The events are k, and well, the function is defined only at integer values of k. So here's k. This is the probability of k, sorry. Yeah, so you have integer values of k, making it a discrete probability distribution. Okay. Figures 1 and 2 are the plots of the probabilities of the distribution in figure 1, and okay, the figure 2 is the cumulative distribution function of, or CDF. Okay, that's why you see it is increasing. Okay, that's the CDF. Okay, again, because this could be presented in tabular form. Now, the formula for this Poisson distribution. Okay, so the function is in terms of the k, the events, okay, in time, all right, it's in time or space, and you have the lambda indicative of the mean rate. Okay, again, this is equal to the, if we are finding the probability of k, okay, and it's the formula is lambda raised to k e. This is the exponential natural exponential number, okay, negative to negative raised to the negative lambda all over the, or all over k factorial. If the events k occur in an interval t, you introduce the function t, the variable t, and it becomes k t, all right, and the formula is rt, right? The quantity raised to k, e raised to negative rt all over k factorial of k. You simply just replace the lambda with rt. The assumptions for the Poisson distribution is that the number of times an event occurs in an interval k can take integer values. Events occur independently. The mean rate at which events occur is independent of any other occurrences, and the events cannot occur at the same time, but at an interval no matter how small, which means there has to be a gap between their occurrence. It's well, different to the incontinuous, where there are no gaps in between. Okay, these are the assumptions. That's why when you are trying to tell if a situation could uh, be applied with the Poisson distribution, these are the assumptions that you have to take note of. All right. Now, we have here an example of a problem in hydrology, in hydrometeorology. Well, if you include meteorology to the hydrology field, and the problem is that the return. Well, we're looking for a model here. If the model, we're looking into the use of the Poisson distribution as a model, and the problem is um, the return period of a typhoon of the same magnitude is 20 years. If you've not heard of the return period, this is a concept in weather and flood forecasting where the shorter the return period means the more probable that a certain natural event is going to occur. And almost common to the natural events is this assumption that it usually takes around 20 years. Now, we want to calculate the probability of the events k, 0, 1, 2, 3, 4, 5, 6, 8, and k is the number of typhoons. And you want to know their probabilities in a 20-year interval. We are going to assume that the Poisson distribution as a model is appropriate, or if it's, well, it could really be used as a model. And so we have the given as shown, the lambda is 1. Why? Because we just have a the mean rate is for a 20-year period is 1. Okay, we have already just identified that here. Okay, the lambda is 1 because the return period is the same magnitude, so 1 in 20 years. Okay, that's the return period. That's why we have 1. Now the k you have here. Now the formula is already given. We have the lambda raised to k times e raised to negative alpha lambda, and all over k factorial. This is very direct, right? Now, to solve for this, we are going to make use of an Excel spreadsheet again, or yeah, spreadsheet software. And what we're going to do is we're going to lay out. Okay, I'm going to share a screen so that we could see that. Okay, I'm going to give this a spreadsheet. Okay. Now you have the screen. I'm sharing it to you. All right, so we have lambda. Okay. Okay, we have the lambda as 1 and k as 1, 0 to 6. Now we want to get the probability of each of these events, and we have it as p x equals k. Oh, sorry, p equals k, and what we will have here is the equation. All right, we have. Let me see again the equation. Okay, I'm not really task. In my opinion, it's not really good to memorize equations, but oftentimes you should. But I'm not really with all all of the equations in the engineering discipline. I just really could not memorize all of them. You just have to be familiar. In any case, okay. So we have here lambda And again, I'm going to make this the same for everything, all the cells. So we're going to raise this to k. This is k. Right times the natural exponent. Okay. The negative of lambda, again, fixed constant, all over k factorial. K, yeah, okay. K factorial, the factorial of 0 is 1, right? Am I correct or not? All right, so that's the final equation, and we're just going to drag this down one down. All right, so that's the probability of all of each of the event we have been talking about, and we want the cumulative distribution function. So we just simply add this one. Okay, equals plus, right? So it's not yet a perfect one. If you increase the k, you could do. Okay, the probability of finding events. Okay, what does the CDF mean? If you if you have an event that is well greater than or equal less than or equal to 6 k. Okay, so uh, if it's less than or equal to 6, you get a 99.9 chance of it occurring. So increasing the event, the probability of having 0 typhoons is 37%. The same with 1. So they have an equal probability of occurrence. But having 2 is 18%. Yeah, 0.18, and it's decreasing as it goes up. But if you're going to see it from the cumulative distribution function, okay, the probability of finding less than or equal to 6 typhoons, sorry, typhoon is and a storm is different. Typhoons in a year, that would be 99.91%, almost 1. Okay, so there's a very likelihood of finding 6, then 5, then 4. Okay, because you're adding up all the probabilities of the other lower values or the events based on the probability theory. Right, in the next lecture, we're going to talk about the continuous random variables, and that would be a okay. So I'll be seeing you in the next lecture on continuous random variables. I'll see you. Thank you for listening.